closest to you, would you please raise your hand? Okay, thanks. We have two up front here. We'll get started in just a minute.
I don't know anybody. Okay. That's why I hate coming down to the main library to take the paper. Trying to go out to the suburbs.
I mean, well, no longer on Sundays. Maybe on Saturdays, some of the, the art times, like if you come down in the evening.
So it's not,
I don't think you have to
You probably don't want it.
No. Ma'am.
I know
Ma'am.
on Sundays.
Well, I guess
They're passing this
Oh,
around.
sorry.
Nobody else can get into the room.
I guess so.
Welcome to the 2016 Tuesday Topics Series. And good afternoon to everyone. Great turnout. Thank you for being here tonight. My name is Rebecca Foose, and I'm with the Friends and Foundation of the Rochester Public Library. I'd like to thank our Tuesday Topics Committee. Lawrence Jones is our chairperson, and the volunteers who are on the committee who come up with the topics and arrange the speakers. And I'd also like to welcome our remote audience today, following us live on Twitter. And we expect to be able to stream Tuesday Topics live, thanks to Alicia Gunther from Rochester Public Library helping us out today, and donors like you for making the technology and programming possible here at the library. So thank you for that. So when our volunteer committee got together, it was pretty unanimous that we wanted to know more about photonics. And we asked each other, what do you know about photonics? Well, we knew it had something to do with science and something to do with light. And it's coming to Rochester, and it's going to be big. And we kind of stopped there. Is anybody else about there? Okay. So we have a three-part series that we are going to present on photonics. Today is the science. Next week is the politics. And third is the effect on the economy for Rochester, the outlook. So today, Paul Ballentine is going to help demystify some of the science of photonics for us. And what better person to do this with 25 years of leadership in engineering, research, business development, and strategic planning in multiple industries. He specializes in technology-driven economic development, optics, photonics, imaging, semiconductors, manufacturing equipment, and clean energy. He's the executive director of the Center for Emerging and Innovative Sciences at the University of Rochester, and principal of Selenium, a clean energy consulting business. He has his PhD from the U of R in electrical engineering, a master's at MIT in mechanical engineering, and his bachelor's in physics from Siena College. Please join me in welcoming Paul Ballentine.
I joke about my well-rounded technical background in Texas. We say we like all kinds of music, country and western. But anyway, when I was getting ready for this, I thought there'd be about 10 people. But I figured a lot of the people here either work for Kodak, Xerox, and Bausch & Lomb, in which case they know much more about the topic than I do, or they don't know much about it at all. So that's kind of a hard audience to satisfy. So I figured instead of talking about optics and photonics, I'd just give a little history lesson. And maybe that's the best way to kind of ease into the topic is to show how over the years the technology has evolved and built on itself from the earliest ancient days of the Greeks to what we have right now with the Institute for Integrated Photonics here in Rochester, which is about as advanced as you can possibly get. So just a word about optics and photonics. You hear these two words, sometimes they're spoken as they're different, sometimes they're interchangeable, and both are true. Both optics and photonics are being described these days as the science and application of light. There's, increase the size of my screen here because my optics are not that good. Now, optics is generally associated with the wave nature of light, with lenses, prisms, mirrors, things like that. Technology that's been around for a very long time. Photonics is a relatively new field. The term photonics was coined in the 1960s, and photonics has to do with the quantum nature of light and dealing with light as particles and all of the technologies that's enabled over the last 100 years or so. So both of these cover everything from the emission of the light to the manipulation, like through lenses, the modulation of it for communications purposes, detecting, like the detectors in the camera, and the signal processing is very important. What do you do with that image after it's captured? The applications of photonics are as broad as the economy and as broad as what we do with our daily lives. Telecommunications, displays, manufacturing equipment, robots and lasers and such, satellite imaging, cameras, defense systems, medical diagnostics and treatment, mobile devices, solid-state lighting, photovoltaics. So you can see, I mean, there's just a very broad range of technologies where photonics plays the central role or a very important role in making these products work. So back to my history lesson. So the use, the manipulation of light goes back as far as recorded history, and I'm sure before then people were using mirrors and things to change the direction of light. But the ancient Greeks did a lot to put that on more of a scientific basis. Euclid and Ptolemy mathematically represented the way light passes through lenses and things and bounces off of objects, and they did a lot to advance the science of optics. An Iranian, Al-Hazan, wrote a seminal work called Optics in 1015, and he is considered by some to be the father of geometric optics. He advanced what the Greeks had done, and he understood really how the eye captured light and focused it onto the retina. Before him, people thought that light was emitted from the eye, and so he did quite a bit to understand that. I note that in the year 1440, Gutenberg developed the printing press. It's not a photonics device, but it'll come back a little bit later in a way that you'll see photonics really touches on all kinds of technologies. Throughout the 1600s, there was a lot of advances in optics and photonics, and astronomy has played a critical role. Optics has enabled astronomy, and astronomy, as you'll see in a minute, has really taught us a lot about optics. And Galileo and Kepler developed telescopes and microscopes by putting lenses together in quite a brilliant way when you think about how long ago that was. Some of the most important mathematical understanding of light was due to Descartes and Snell. In particular, Snell put on a mathematical basis the way light is bent when it passes from one medium to another. And that's the basic of lenses. It's called Snell's law, and understood things like the refractive index of the material, where that determines how much the light is bent. So that was really an important step in understanding the lenses, and that's based on refraction. So you have reflection, and you have refraction from lenses, and there's another kind of manipulation, which you'll see in a second. Now, people began to understand that light can be represented by waves. Just like you have waves in water, if you consider light to be waves, then you can explain a lot of things, like you can explain this refractive behavior interference patterns and things like that that people were seeing. So Huygens, known for Huygens' principle, and Grimaldi, and these two discovered that when light passes through a tiny slit, it spreads out, and that's called diffraction. And that's used for things like Fresnel lenses, which you may see on the old-fashioned overhead projector, and concentric lines to change the direction of light. So you've got reflection, refraction, and diffraction are three technologies that are used in optics to manipulate light. Now, Newton, perhaps the greatest physicist that ever lived, in addition to doing his work on gravity, did a lot of work on optics and passed light through a prism and saw the light expanding and coined the term spectrum and began to understand that the light that we see, the white light, is actually composed of a bunch of different colors. So he really advanced the technology quite a bit. Interestingly, he thought that light was particles, and he proceeded to say, I can explain all of this based on light being particles. Now, it turns out this very premonition, because later on we'll talk about the particle aspect of light, but he was proved wrong at that point in time, because basically everything that was being observed could be mathematically modeled as waves. So for the next few hundred years, light continued to be considered waves only. Now, we know that light propagates very fast. That's why it's useful for communication purposes. You know it travels fast because if you see someone drop a stone or do something a long ways away, the image gets to you much quicker than the sound. So light travels much faster than the speed of sound. So what I was saying earlier about astronomy, yes, lenses and such were used to enable astronomy, but he actually used observations from Eon, I think it is, the moon around Jupiter, and measuring the time that things happen. And he was the first person to ever prove that light has a finite speed, and he calculated light. He was off by about 25%, which is not bad for the first experiment. Later on, through some more accurate measurements, light is 300 million meters per second, which is about 187,000 miles per second. So it's definitely a very fast way to get information from point A to point B. And these developments, as I was putting all this stuff down, it reminded me that each of these inventions builds on the previous inventions. And by the time 1800, we're talking about 2,000 years of invention, and that's what libraries are all about, right? Libraries are the repository of knowledge, so that people can pick up where other people left off and go make advances that could never be made in a single lifetime. Now, Fresnel developed the Fresnel lens, which is the object, the lens you see on an overhead projector, and he used the principle of interference to do that. So you've all seen, maybe you've seen fringes, when you have two pieces of transparent material that are very close together. You see black and white lines, black and white circles, and that has to do with the wave nature of light and how when waves are in phase, they amplify one another, and when they're 180 degrees out of phase, they cancel one another. And so if there's two waves that are impinging on a surface, depending on whether they're in phase or out of phase, you get black lines on that light that's projected. Another important discovery was Fraunhofer, a brilliant German physicist, who was looking at radiation from the sun, and he broke up the spectrum, and he saw actually that there's dark bands in the spectrum. And these dark bands are due to the fact that certain colors of light, certain wavelengths, are absorbed by substances in the sun and substances in the air. And so that was the discovery of spectroscopy. And spectroscopy is extremely powerful today because it's used to identify chemicals for all kinds of purposes. So there's one important application of photonics and optics is spectroscopy. Now, throughout this talk, I'll be weaving in conversations about Rochester and some of the most important developments in optics and photonics were made here in Rochester. So in 1853, Bausch & Lomb was formed here, and their major contribution, a lot of contributions, was that they made eyeglasses affordable to a lot of people. And they perfected creating the lenses and using rubber material as the frames. One of the most important discoveries in optics, and in fact one of the most important discoveries in all of physics, is in the middle of the 1800s, James Clerk Maxwell modeled radiation as waves, and he understood that electric fields and magnetic fields combine to form a wave that propagates by itself. Before that, people thought that light passed through some substance in the air called ether, and you needed the ether to have a wave, right? You can't just have a wave without nothing to jiggle up and down. But he took all the knowledge we had about the way electric fields and magnetic fields interact, and he mathematically derived a formula that says that the electromagnetic fields propagate forward without any ether. And so that was radio waves. Now, Corning was also very important in the field of optics. They were actually established 2 years before Bausch & Lomb, and eventually became the company Corning in Corning, New York. But one of the things they did was they made glass. That was not good. They made glass for Edison's light bulb. So Edison couldn't sell a lot of light bulbs unless he had a way of mass producing the glass, and Corning had a critical role in that. Now, in order to prove Maxwell's theory of propagation, Hertz measured the speed of the electromagnetic waves, and it turned out to be the exact same as the speed of light. And so Maxwell then understood that light is nothing more than a part of the electromagnetic spectrum. And blow that up a bit, and there's a factor of 10 to the 20th in the frequency or the wavelength of radiation that we can detect. Everything from gamma rays, cosmic waves, all the way down to a very low frequency of ultra low frequency radio waves, ultra long wavelength radio waves. And what we see is only about a factor of 2. It's only about 400 to 700 nanometers. So our eyes can only see, 1 millionth of 1 millionth of 1 millionth of the radiation that exists. So we can do a lot with expanding on that, which we'll see we have. So enter the 1900s, and more discoveries of photonics, but also more use of it in a more technical sense. So one of the most important ones was Kodak, and Eastman did for photography what Bausch & Lomb did for eyeglasses, made it affordable to a lot of people, and in order to have photography, you need lenses and things like that. So a lot of development in lenses took place here in Rochester. Now, the first couple of decades of the 20th century were remarkable from a physics point of view. There was just a whole bunch of brilliant physicists living at the same time: Planck, Bohr, Einstein, Schrodinger, Heisenberg, Fermi, etc. And they all together discovered quantum mechanics, which says that matter is not only a particle, but it's a wave as well. So an electron was thought to be just a particle going around an atom, and they understood that that's also a wave. That also applies to light. And so they coined the term photon, which photos is the Greek word for light, an electron. So an optical electron is a photon. And that was the fundamental discovery that enabled the modern photonics. So now there was an effect that helped Einstein understand that, not the photoelectric effect, which is similar to photovoltaic. Light was coming on to a substance, and electrons were coming off. And so in order to understand that, you needed to explain that the light that's coming on is a particle that's kicking off the electrons. Now, it wasn't too far after that Einstein says, well, geez, this light ought to be able to amplify itself, stimulated emission, it's called. And so he predicted the laser, light amplification by stimulation of emitted radiation. And it wouldn't be for some time after that we were able to make a laser. But again, what a brilliant man. I mean, just revolutionized things and saw things that people couldn't do for decades. Another important photonics revolution that took place, not in Rochester, but was moved to Rochester, was Carlson's invention of xerography. This technology fundamentally requires a lot of optics in order to create. So you have Kodak, you have Bausch & Lomb, you have Corning, you have Xerox. I mean, Rochester really is the center of evolution of optics and photonics in the 20th and hopefully the 21st century. Now, there was another development in the 1940s that was not quite photonic, but it proved to be critical for photonics, and that is the invention of the transistor, which led to the integrated circuit. And the transistor was developed based on quantum mechanics, based on the quantum nature of electrons and atoms. And that then is used to create a whole bunch of things, such as the modern photovoltaic cell. Before that, photovoltaic cells were very crude. Bell Labs and RCA produced a functional and economically viable photovoltaic device. So just a few years later, finally, Towns and Shallow made the first laser. And they started out with microwave amplification of light, and then they finally did it for optical radiation. And the laser was born. So here you have Bell Labs. They invented the transistor. They perfected the solar cell. They invented the laser. Bell Labs is central to a whole lot of developments in photonics, perhaps the company that is most central. And that's because they're a communication company. And light is really good for communications. So that's we'll see a little bit better where that comes in. Now, transferring, so another important discovery, another important development is flat panel displays. And the seminal invention there was the plasma display that was invented at the University of Illinois. And that, again, takes a whole lot of optics and photonics to create these images and project them. So that's another important development. Another major development was, we knew that light could be very useful for communications, but free space light is really not. So channeling the light is important. And people have been working on channeling light propagation for a long time, even through a stream of water. But Bell Labs is the company that really launched the optical fiber communications industry, and they saw the ability to transmit much higher data rates in many fewer wires, and that was a seminal development. The IMAX is another example, IMAX movies. Throughout all this time, cinematography was being developed, a lot of it here in Rochester at Kodak, and IMAX in 1967 at the Montreal World's Fair showed their first IMAX. And I put that up because the most recent IMAX projector, based on lasers, was developed here and is being developed here in Rochester. Kodak spun out its digital cinema business. IMAX bought that. IMAX tried to pull that into Canada. They found out that they can't do this development anywhere else but here, where all the precision optics and machine shops are. And so that technology, a lot of people don't know that, is the new generation of IMAX projectors is being done here in Rochester. Now, Corning, of course, a glass manufacturer, plays a huge role in fiber optics. They make, I don't know what percentage, but a very high percentage of fiber optics. And the problem with earlier fiber optics is the light was attenuated too quickly. It was pretty good, but it wanted to go meters. And through very sophisticated technology and manufacturing process development, Corning developed processes to draw glass and propagate it for kilometers and eventually many kilometers. So Corning, again, is central to the whole photonics revolution. Two more inventions in Rochester that are critical to photonics is the first digital camera, invented by Steve Sasson at Kodak in 1975. And along with that, the Bayer color filter array, which is used to this day on all color digital cameras. Fundamental invention that allows you to take colored light and break it into different parts so that you can take those digital signals separately for red, green, and yellow and recombine it. So that, if that doesn't kind of get you feeling good about the history of Rochester and photonics, it's no wonder why this institute is based here. Another important development is optical character recognition. And that technology was not developed here in Rochester, but Xerox acquired it from a guy named Ray Kurzweil and brought it here and developed optical character recognition software and equipment, spun out a company called Kurtas. And Kurtas' technology actually was used to digitize a lot of books here in the Rochester City Library. And one of the books is, in fact, a book of the 1916 Chamber of Commerce publication that went on to say that Rochester was number one in the entire nation in manufacturing output per capita. That's an astonishing fact. And they continued to do so for the entire 20th century, almost. And that was based largely on Kodak's business, but and as well as the other companies here. So not only is photonics, not only is Rochester very important to photonics, but photonics has been very important to Rochester, of course. Another important development was glass for the flat panel display. And again, Corning comes in and develops a fusion process of drawing this glass. I keep doing that, sorry. Drawing this glass from a big vat to tiny little sheets, and are able to do so with incredible control of thickness and surface finish. And these big glass plants now are built right adjacent to the big flat panel factories. So the glass moves from the Corning plant into the Samsung plant in an underground or above ground chamber. Now, more developments here in Rochester. In addition to the first digital camera, the first digital SLR camera was developed at Kodak in '87. It's a Nikon body that they used, but it was the Kodak technology. Also, a revolutionary technology was OLED. So we had, light-emitting diodes, solid-state light-emitting diodes, and plasma displays. Kodak, being a chemically oriented company, did a lot of work on developing a organic light-emitting diode, and it's very early work. So Ching Tang, who's still here, professor at the University of Rochester, invented that, and now you're seeing OLEDs in a lot of products. Kodak sold that technology to LG. Another important technology that was developed here is magnetorheological finishing, MRF. And this was something that allowed lenses to be made with much more precision and much more predictability than was able to be made before. And that technology was developed at the University of Rochester, and it was spun out into a company called QED, which makes the equipment today. And that's a picture of a QED machine. So that's another side of Rochester which is extremely important, is the advancement in the state-of-the-art of optics manufacturing. And Rochester is probably the highest concentration of optics manufacturers in the world. There's about 50 optics companies within about a 20-mile radius here of Rochester. So it's very important for our economy, and Rochester really enables a lot of space telescopes and lithography machines and things like that. So today, fiber optics is, and the electronics, electro-optics behind it, is to the point where it can transmit more than 10 terabits per second. And that really is what enables the internet. Couldn't use the internet without photonics. Couldn't have the internet without optical fiber. It would be so slow, it would be as slow as dial-up, and none of what we are comfortable with using today would be here. So that's kind of a tour through some of the history of optics and photonics, and you can see where they kind of blend together. Photonics devices like lasers require lenses and optics, and optical technologies enable a lot of photonics. Now, one of the main uses of photonics is communications. And communications started out, there's been optical communications as early as the ancient Greeks, where they used light signals. There's these hydraulic semaphores that transmitted signals from one mountain to the next, people to communicate. And even to this day, in naval applications and in lighthouses, free space optics is used. Now, the Gutenberg press is another form of communications. It was books as a means of communication. The invention of the telegraph by Samuel Morse, and the development of typewriters, and the invention of the telephone. So these are all forms of communication as well. But what really makes telephony practical today is that it's using optical technologies. So optics has taken the early inventions and brought it to the new level. In terms of the written word, you go from Gutenberg's press and typewriters to high-speed document printers and imagers today. So now it's clearly a photonics, so books now rely on photonics and light for their production and scanning and reproduction. And today, what do you have? You have the Kindle, you have mobile phones, you have data centers. There's, millions of lasers in these data centers, tiny lasers that initiate the light and fiber optics. And you have, satellites. So in terms of communications, the history of communications, today, communications is strongly enabled by photonics. Now, what is integrated photonics? So this institute that we're talking about is an institute for integrated photonics. So if you think of photonics is the combination of optics and electronics. So you take standard electronics and you bring optics with it, and you create things like lasers and photovoltaic cells and solid-state lights and things like that. In the meantime, electronics itself was revolutionized with integrated electronics that was built on this transistor at Bell Labs. So you had manufacturing processes that were used to increase the amount of transistors and information processing capability on a piece of silicon, and it follows Moore's law, which started in the 60s, and it says that the amount of transistors and the amount of information doubles every 2 years. And so the state-of-the-art chips today have 5 billion transistors on them. And if one of them doesn't work, you throw the thing away. So the technology that goes into manufacturing is staggering. There's a plant in Malta, New York, the Global Foundries plant. It costs $10 billion. How can you have a building that costs $10 billion? But that shows you the amount of equipment in there and the precision that allows them to create integrated electronics. So what is integrated photonics? Well, integrated photonics simply takes photonics, which is sort of on a macro scale, lasers and fibers and things, and applies the manufacturing processes that are used for integrated electronics to photonics. So now you have tiny little tiny little pathways of light that move light around, and these are put on pieces of silicon that are similar to that. Here we see that this is the integrated circuit, but what you see is a package. So the integrated circuit has to be put inside a package, right, in order to connect it to the circuit board. The same thing with integrated photonics. You have the integrated photonic circuit with their devices. This, by the way, was done at RIT. Both of these were done by Stefan Preble at RIT. But you need packaging as well. And what packaging does is allows you to bring hundreds of fibers into a tiny little device in and out. So now what you have is truly integrated photonics. Fiber optics coming in, a lot of processing using optical and electronic signals, and light signals coming out. The applications for integrated photonics are varied: telecom, datacom, high-speed radar, sensors, biosensors, and something called LiDAR, light detection and ranging. And that's going to be used for automobiles in the future. They're going to use that to avoid collisions and things like that. So this same photonics is it's focused on integrated photonics. The universities that are involved are SUNY Poly, University of Rochester, RIT, MIT, University of California, Santa Barbara, University of Arizona. A lot of major companies involved. It's focused on manufacturing, so not so much on technology development, like developing a new switch or something, but how do you make these integrated photonics? Because right now they're prohibitively expensive to make. There's various steps in that manufacturing process. You have to design the thing. You have to produce the wafer. There's a wafer. There's a sample wafer made by Corning over there. And you have to package it, you have to test it, and things like that. And so there's 4 areas of AIM Photonics, 4 manufacturing divisions. And there's 4 applications that they're working on: datacom, RF, sensors, and LiDAR. So it's kind of a 4x4 matrix. There's also a workforce training part to it. So in Rochester is the home to the headquarters of the whole thing, the test and packaging, which is very important, and the sensors, because it builds off of a lot of biological sensing work done at the University of Rochester Medical Center. The challenge, though, is there are no integrated photonics companies in Rochester today. So that's both a challenge and an opportunity. Right? We can't just step in, and it's not going to help grow a lot of companies because they don't exist. But it's extremely important that we jump on that, right? Because it's the future. And the integration of electronics and photonics is going to enable things that we can't even imagine right now. And so what we want to do is start to create those kind of companies in Rochester, or take existing companies and move them into that, or take companies and bring them into the area. Imaging is another major theme throughout what I was saying. Back in the earliest days of photography, the invention of photography, the Brownie camera, advances in cameras, the first digital camera, the first high-speed printer. And what you see here is the number of pictures taken each year as the function of time. And this is about 2010, I think. And what you see is film just dropped off the cliff. And it can't compete with digital. And so, unfortunately, Rochester was on this bandwagon, and the rest of the world was on that bandwagon. And even though Kodak invented the digital camera, it did not take advantage of that. So, we've got to get on that bandwagon. And we are. And so, modern digital imaging, here's a picture of Hurricane Sandy taken by an Maxwells camera. Rochester is right over there in the corner. Here's the Boston bomber, a video camera. Here's the same guy laying underneath the tarp in a boat that they took from a helicopter using infrared imaging. Remember I was saying that the optical spectrum is just a tiny part of the electromagnetic spectrum. We're expanding that. We're taking infrared pictures now, which is a longer wavelength, and terahertz, which is even longer, and ultraviolet, which is shorter. So we're expanding the ability of humans to see radiation through new technologies. And everything you see today really is building on all these inventions, a lot of the technology. There's Obama's Facebook page. Instagram. This is the IMAX projector. Those are the new laser-based. Here's a 615, a company in Rochester, a small company that's spun out of Vuzix. They're doing DoD 3D displays, virtual reality. So you can see the future is really bright for photonics and imaging. And there's no reason why Rochester can't really participate in that. Am I out of time? I'm 1 minute, right? Okay. So because the Photonics Institute is around integrated photonics, and it only leverages a very small sliver of capability, the groups that are working on the $500 million Regional Economic Development Council investments, the Optics and Photonics group is putting forward ideas for a second institute, center, consortium. I don't know quite what to call it yet, but it would work on 3 other areas. It can't work on everything, but it would work on optics, lasers, and imaging. And it builds on our industrial strengths, the Laboratory for Laser Energetics, the 50 optics companies, all of the imaging capital of the world. So what we want to do is take our strengths there and use the evolution of digital technology to advance, to grow the Rochester economy and to return it to its preeminence in photonics, and to make Rochester truly the photonics capital of the world. We can do this. It leverages AIM photonics because a lot of the devices that are going to be developed are used in imaging systems, and a lot of the lasers are used to fabricate integrated photonics, so there's a lot of synergy there. There's big companies that we're talking to. I don't put their name up there because we're not to that point yet, but you know who they are, the usual cast of characters, and they're all very interested in this. So, and for different reasons, which is good because they can work together and not compete with one another. The small companies, we had a meeting on Friday of 50 photonics companies at the University of Rochester, and it was a really remarkable meeting. The CEOs of each one of those 50 companies had 2 minutes to describe what they do to everyone else.
2 minutes.
And we, after 50 2-minute talks, we ended 30 seconds early. So I got to give it to these guys. Of course, one guy went on for 15 minutes, and everybody only had 1 minute. They did pretty good. And that meeting was called to figure out, geez, we've got these big opportunities, AIM Photonics and this new institute, but how do we participate? We're too small. So the idea, we called it a speed dating, a beauty pageant followed by a speed dating. But it was neither a beauty pageant nor a speed dating, but it was a good networking. And imaging, we're really excited about the imaging part because that's where the big dollars are. It's the systems. Integrated photonic devices are good, but they're chips. Lenses are good, but they're components, right? But what did Xerox and Kodak and Bausch & Lomb do? They sold final products. Very high dollar value end products, high profit margins, and also the systems control the component development. So when we're only developing components in Rochester, we're responding to what Apple tells us to do, or Google. What we want to do is build this end system capability so that we can actually control our own destiny. It'll leverage the University of Rochester and RIT. We have a proposed name, the Light Scale Research Institute. Light is the basis of it, and scale, meaning we want to take technologies and not do something that's going to result in a $10 million or $100 million industry. We want $1 billion industries to come out of the technologies that we develop. So that's where we're at, and that's it. Thank you very much. There's this year marks the 100th anniversary of the Optical Society of America. In 1916, the OSA was established here in Rochester as a result of a concern that George Eastman had about in World War I, there wasn't a lot of good optics capability here. So the OSA is the 100th anniversary. Now the OSA does outreach, and they have this thing called the optics toolkit, which you can come up and take a look at. And it's things for middle schoolers, and it demonstrates things like Fresnel diffraction lenses and birefringent interference and things like that. So the local OSA chapter builds these things from donations and dues and takes them out to dozens of junior high school classes and does lectures on that. As I said, I've got a wafer from Corning you could take a look at. That's what the Photonics devices are made on. I have annual reports from my center, the CEIS, for you to take a look at. We developed this poster here as kind of like a patriotic promotional poster that shows you how many photonics companies there are in Rochester. Now, it's kind of a cartoon map. It reminds me of the map of the United States from Texas, where Texas is like 90%. Well, Rochester Photonics is 90% of New York State Photonics. And so we had to distort the shape of that. But we have some leftover from last year. Last year was a major year for optics, the International Year of Light. You're welcome to take those as well. Thank you.
You mentioned the integrated photonics companies and the fact that we have them here. Where are they located in terms of the main focus?
Sorry.
Silicon Valley, in Boston, that.
Silicon Valley, MIT does a lot of work.
God.
Bell Labs, well, what's left of that, yes. Mostly California, southern and
So when you talk about establishing maybe Rochester as integrated photonics company, are they starting from scratch, or would the process be encouraging those companies here?
Oh.
Okay.
We're out of time, so just come on up and ask me questions, or you can ask now if you want.
Oh, out loud? For everybody or just me?
I think I went too long.
Do it from there. We can
Okay, yeah. The question I have is, what advantage is there in photonics over an integrated circuit? All you're doing, are you just doing the same thing on the circuit board with light that you were originally doing with the printed, or
Light propagates faster than electricity.
okay, so it's faster, less power, less heat.
And it's small. Because these data centers have so many wires around.
Right. Okay.
It's faster, lower power.
Does it do? Can it do something completely different though? Don't know yet. Okay. Thank you.
Thank you for joining. Join us on Tuesday, next Tuesday for Photonics 2.